Welcome everyone. In this video we are going to talk about the last microwave diode in our series, which is the tunnel diode. The tunnel diode is a VN junction diode, but in this case we are using B plus N plus junction, such that we use highly doped BN junction, and such highly doped BN junction will introduce a very small depletion region between the V and N, in the junction between the V and N. And the tunnel diode is usually used in forward biased. And effectively, the main tunneling effect is mainly introduced at the nonlinear region at very small forward biasing voltage. So we say that the tunnel diode is a VN junction diode with a doping profile that allows electrons tunnel through a narrow band gap, and this tunneling effect is leading to a negative resistance at high frequency. And we will see how this tunneling mechanism is obtained. The VN junction of the tunnel diode is highly doped. So the main characteristic of tunnel diodes, they are highly doped junction, from positive to negative, and it has very small depletion region, around few nanometers. Normally these diodes are constructed with germanium, and they can also be created with gallium arsenide or silicon. The energy band of the tunnel diode looks like this. We have B plus connected to N plus. So the energy level for both the valence band and the conduction band for the B type part is much higher than the Fermi level. On the other hand, the energy bands for the N plus type is much lower than the Fermi level. Now, if we are going to apply forward bias for such BN junction, so we are applying negative here and positive here. In this case, the negative voltage at the side of the N type will push the electrons in this direction, away from the negative. Effectively, this is very narrow band gap. So if I have sufficient energy, the electrons can be transferred from the conduction band of the N-type piece to the valence band of the B-type piece. That's what we are calling tunneling electrons. So if we have a small voltage provided, some electrons will tunnel from the conduction band of the N-type to the valence band of the B-type. These tunneling electrons will introduce small current. So we have a small current. And as we are increasing the forward bias voltage, this tunneling electrons or this tunneling current will increase. Now, by increasing the negative voltage here, it means that we are going to increase up the energy of the N type and decrease type the energy of the B type. Or in other words, we are going to decrease the difference between the energy of the B type sample and the N type sample. So by increasing the forward voltage, the conduction band and the valence band of the N type will be rising up towards the Fermi level, and the conduction band and the valence band of the B type will be going down towards the Fermi level. And as long as we increasing the potential, we are increasing the energy, so we have some tunnel electrons. After a while, the conduction band of the N type will be nearly at the same level of the valence band. So in this case, the opportunity of tunneling electron will be decreased because we have a less direct way from the conduction band to the valence band of the B type in this case. So in this case, the current or the tunneling current it would be decreased. So with increasing the forward voltage after a certain point, the tunneling current will be decreasing instead of increasing, because the conduction band here has been increased, and the opportunity of transferring electrons from the conduction band of the N type to tunnel to the valence band of the P type will be decreased in this case. After a certain region, uh, the tunneling effect will stop completely. But at this stage, the conduction electron or the conduction band of the N type has been decreased enough such that the electron will be transferred from the conduction band of the N type to the conduction band of the P type, which is the usual mechanism for the P-N junction. So in this case, the current will begin to increase once again by increasing the voltage, but the mechanism here is not due to the tunneling effect, but is due to the transfer from the conduction band of N type to the conduction band of the P type. So the current or the IV characteristic of the tunnel diode, it would look like this. At the beginning, it would be completely tunneling current, and after a while, the tunneling current will be decreased until I reach to a certain level such that the current will be a forward or normal forward current. In this region, when the tunnel current reaches to the maximum and it starts to decrease, in this region, the dynamic resistance of the tunnel diode is negative resistance. It is similar to the same effect of the gun diode. So we have a negative dynamic resistance in this region, and this negative dynamic resistance, it can be used as a microwave oscillator, it can be used as a microwave amplifier, and so on. So we have a similar IV characteristic to the gun diode, but with a completely different mechanism. So in conclusion, the IV characteristics of the tunnel diode is, at the beginning we have tunneling current, and we reach to a peak point at a voltage V peak at the point A. After this peak point, we have a negative resistance region until to a valley point where the tunnel current is decreased or is decreasing by increasing the applied voltage until the tunnel current vanishes completely, and then we have the conventional forward current. The operating region of the tunnel diode in the negative resistance region between the peak point and the valley point, or from the point A to the point B. And in this region, the equivalent circuit for the tunnel diode is simply a series resistance due to the leads of the tunnel diode with a negative resistance correspond to the negative dynamic resistance here, in parallel with a capacitance, which is effectively the capacitance due to the depletion region between the P and N junction, because the depletion region in this case has not been vanished completely. So we have a negative resistance in parallel with a capacitor. In addition to a series inductance, this series inductance is also due to the leads of the tunnel diode. So this is a complete equivalent circuit of the tunnel diode, and the dominant term of this equivalent circuit is a negative resistance in this case. So we say that the tunnel diode microwave circuits, tunnel diodes can be used for oscillators as well as for amplifiers. For oscillators, it is quite similar to the gun diode, the input diode, the barrel diode. If I have a negative resistance and I have included this negative resistance inside a resonant circuit, if I have included the negative resistance inside a resonant circuit, and I have added a DC voltage, so the resonant circuit will oscillate with sustainable oscillation. Also, tunnel diodes can be used as an amplifier, especially low noise amplifier. And before high frequency transistors were available, tunnel diodes provide only the only means for high frequency amplification with solid state devices. Me myself, I have seen a tunnel low noise amplifier for satellite communication system. This was at nearly 1989. Such an amplifier employs the diode in one port reflection circuit. For example, the diode is connected to a circulator, so the input power is incident from port 1, and the power is transferred from port 1 to port 2. At port 2, I have the tunnel diode. The tunnel diode is used as a reflector at this case, and because it has negative resistance, the amplitude of the reflection coefficient is greater than unity. So the reflected signal is greater than the incident signal. The reflected signal from port 2 is going to port 3 through the circulator, so the output of the amplifier is going from port 3. This is effectively a simple structure for an amplifier by using a tunnel diode as a reflector. So such an amplifier employs the diode in one port reflection circuit, where the negative RF resistance of the device produces reflection coefficient with a magnitude greater than unity. And in the lecture of the GaN diode, we have discussed how the negative resistance will introduce a reflection coefficient with magnitude greater than unity, which means that amplification, and therefore amplification of incident signal. Such amplifiers have been made obsolete by modern RF and microwave transistors. However, tunnel diodes are still used in some applications, especially for microwave oscillators, for example. As an example of tunnel diode parallel resonant circuit, we have here a parallel resonant circuit RLC, where R here is positive. If I have connected DC voltage to this parallel resonant circuit, we will have damped oscillations. This damped oscillation is damped mainly due to the presence of the series or the parallel resistance RB. If I have compensated the parallel resistance with a negative resistance, this oscillation can be sustainable, and we have a constant magnitude oscillation. So if I have added a tunnel diode with an equivalent negative resistance in series with this tank circuit, this tunnel diode will compensate the dissipation effect of the parallel resistance. So the output voltage in this case, it would be continuous oscillation. This is how to introduce a simple microwave oscillator by using a tunnel diode. And in this case, it is required to adjust the biasing point of the tunnel diode to be exactly at the beginning of the negative resistance region. So we should use a biasing network to adjust the IV characteristic of the tunnel diode to be at the beginning of the negative resistance region. In this case, the equivalent or the dynamic resistance or the AC resistance of the tunnel diode would be negative, which will compensate the dissipated power at the parallel resistance at this tank circuit. And in this case, we will have a continuous wave or a continuous oscillation. This is briefly what is meant by tunnel diode and how we can use a tunnel diode for a resonant circuit, and what are the main applications for the tunnel diode in the past and nowadays. By this end, we have completed our discussion about microwave diodes. In the following video, we are going to start a brief description of microwave transistors and how to describe or how to specify the parameters of microwave transistors, and how to describe microwave transistor is essential part in how to design microwave transistors in microwave amplifiers and microwave oscillators, as we will see in the following chapter. So see you in the next video in microwave transistors, and as we will see, we will have a bipolar junction transistor and field effect transistor. We will see this in the next video.